Hello, this is Kevin Buzzard and I'm going to go through the solutions to sheet 1 of section 6 of my Formalising Mathematics course. Section 6 is about quotients, but in fact I guess most of the problems I'm going to solve are not really about quotients, they're somehow about integers, because before we make the quotient by an equivalence relation, we've got to prove that the thing we're working with is an equivalence relation. So this is where we're starting here. We're defining a proposition R of A, B. A and B are integers, and the proposition is that they're congruent mod 37. Their difference is a multiple of 37. So we've got to prove, in this sheet, we're basically going to prove that it's an equivalence relation. So we're going to prove it's reflexive, symmetric, and transitive. So there's the definition of R. And if you like, so we've got to prove it's reflexive, and if you don't know what reflexive means, or you've forgotten what it means, or you want to know what Lean thinks it means, we could start by unfolding reflexive. And now our goal is a for all, so we can make progress with intro. And now our goal is this R, and so I made this lemma R def, rewrite R def, and now you can see what the goal is. So we've got to prove reflexivity of this relation. We've got to prove that x is an integer, then x is congruent to x modulo 37, or more precisely, that there exists an integer z such that x minus x is 37 times that integer. But of course x minus x is 0. So the integer z should be 0, so we can put u 0. And now we've got to prove that x minus x is 37 times 0, and that's the kind of thing that the ring tactic should be able to do. So that's the proof of that. And of course, we don't need the unfold, and we also don't need the rewrite, because that's definitional as well. So there's a complete proof that it's reflective. Symmetry is a little bit harder. I mean, let's just not worry about, let's just go straight with intros. What does symmetry say? It says if x is related to y, then y is related to x. So it's going to be intros x and y, and then a hypothesis h that says x is related to y. Now, of course, we can rewrite R def at h and at the goal, and there's the exists. So now we've got a hypothesis that there exists an integer with some property, and we're trying to prove that there exists an integer with some property. So we can take the h apart, right? Case is h. With AHA. So there, now our hypothesis HA says that x minus y is 37 times A, and we've got to come up with an integer z such that y minus x is 37 times that integer. And of course, if you think about it, that integer is going to be negative A, so we can use negative A. And now we've got a situation that it kind of looks like this is just a question in ring theory, right? X minus y is 37 times A, and we've got to prove that y minus x is 37 times negative A. So you kind of think, great, the ring tactic should try that, but I should solve that. But you see, the ring tactic doesn't do it. We've still got a goal left. And so what's going on? Why doesn't the ring tactic solve this? And that's because the ring tactic doesn't do this job. The ring tactic proves identities in ring theory. The thing that the ring tactic would do, it would prove that y minus x is negative x minus y. The ring tactic doesn't ever use hypotheses, so it would only prove a goal if the goal was sort of directly true without having to use any hypotheses. And right now we have to use hypothesis HA. The goal sort of isn't true by itself, right? If we cleared hypothesis HA, then this goal wouldn't be solvable at all, right? That's a step in the wrong direction. So we're gonna, if we want to use the ring tactic, we're going to have to figure out how to use hypothesis HA. So, for example, did you notice that when we tried the ring tactic, it did change the right hand side? 37 times negative A got changed to negative 37 times A. In fact, I wonder if the simplifier will do that. Yeah, the simplifier does that. It believes that negative 37A is a sort of a better sort of normal form than 37 times negative A. So once we've run the simplifier, now you can see the right hand side of HA is in there. So now we could rewrite HA that way. If we did it without the arrow, it would try to find an x minus y, and there isn't one. but we do it with the left arrow, so it finds a 37 minus a, and now the ring tactic will do that one as well. So that's the end of that one. Maybe I could show you another way of doing this. We know that 37 times negative a is negative 37 times a, so we could use halves to do it instead of relying on the simplifier. You know, in some sense we were lucky that the simplifier simplified the goal into a state where we could actually do the rewrite directly. If that hadn't happened, we would have had to somehow do the job ourselves. So we could do this. We could sort of say have hypothesis H. I claim that 37 times negative a equals minus 37 times a. There. So we could make that hypothesis. Now we've got two goals, you see. But that second hypothesis we can just solve by ring immediately. And now we don't need the simplifier anymore. Now what can we do? Now we can rewrite H, you see. There. And then we can rewrite HA. So there we go. The proof's compiling again. So that's a proof that doesn't use the simplifier at all. It just uses ring. But my objection to this proof is that it sort of adds this extra random hypothesis H that we don't actually ever want. We just create it and then immediately rewrite it. And there is a way of making that rewrite happen without ever even creating the hypothesis. That we could do rewrite show 37 times minus a equals minus 37 times a by ring. There we go. So this is kind of nice because now we never had to make that hypothesis HA. We sort of created it temporarily here, and we created we wrote the type here. We created the term with the ring tactic, and then we rewrote the term, and it never ended up in the tactic state. And now we can actually put these together, right? We could rewrite that, and we could rewrite that at the same time. There we go. So there's a proof which is kind of slightly shorter. Maybe I'll leave it like that. Perhaps that's an illustrative use of this show trick. So what have we got to do now? We've got to prove transitivity, and that's going to say if x and y and z are integers, and x is related to y and y is related to z. So we could do. Why don't we use Rintros this time? Let's do this in a more high-powered way. Rintros x, y, and z, and h, and hx, y, and hy, z is probably, yeah. But the thing about, you see here we did an intros and a cases, right? That rewrite's not necessary, right? You don't need to do it. The proof still works. You see, we've got no errors. I'm always looking down here we've got two warnings because we've got two sorries still, but we've got no errors. I just fiddled with the proof that was already working, but I just checked to see that it's still working. So this R isn't exist, right? R def just turns, the definition of R is, there exists something such that blah, blah, blah. And so we can just do the cases directly. We could do it here, right? We could do A, H, A. And then, you see now we don't have an H, you see we don't have an HXY at all. We've just directly got the statement that x minus y is 37a. And so we could do the same here. BHB. There. So we know x minus y is 37a and y minus z is 37b. And we've got let's just use nothing. And does that work? We can't do that. Hard luck. Exist sign nothing will probably work. Yeah. We're trying to prove that x minus z. I'm just cheating. I'm yet to fill in that underscore. Exist sign is another version of use that will take an underscore. Which means we haven't filled it in. Do you see we've got a dodgy goal now? We've got a goal that isn't a true-false statement. So we're missing an integer, and that's that integer there. So x minus y is 37a, y minus z is 37b, and we've got to prove that x minus z is 37 something. And I guess adding the equations, we see that this is a minus b. So it's a plus b. So it's that. We don't have to use exist sign now. We can go back to using the more normal tactic. We can use a plus b. And now what? So it's the same problem as before. You see, we can't do the rewrite because we haven't got a 37a and we haven't got a 37b. We've got a 37a plus b. But this is so I think the next thing to do is apply distributivity of multiplication over addition. So that's rewrite. It's called mull-add. You see, and now we can rewrite the HA and the HB. So we could do this there, left HA, left HB. And now what's left? I wonder if the simplify would do it. Yeah, it does. We don't. I mean, ring would do it for sure. There you go. Ring's done it, but the simplifier does it as well. And so that means that instead of the rewrite and then the sim, we could probably just use the simplifier. Yeah. We can just use the simplifier. Like that, and in fact probably we don't even have to use we could probably do exact and then pointy brackets a plus b comma and then put this here. Now we wrote exact, so we're back in back in term mode, so I'll put by to put us back in tactic mode. There we go. So there's a highly compressed proof. And now what? We've got to prove that R is an equivalence relation. Well, what's an equivalence relation? Well, that's, I guess, I mean, it's reflexive, symmetric and transitive, but what does Lean think an equivalence relation is? So let's unfold equivalence. Oh, there you go. So Lean, literally, the definition of equivalence is literally reflexive and symmetric and transitive. So we could split it. And now we've got two goals. We've got to prove reflexive. And the proof of reflexive, so the statement that it's reflexive is called reflexive R, and the proof that it's reflexive is called R reflexive. Right, the name of the lemma is the name of the proof. Right, that colon there, that's the term. R reflexive is the term, and reflexive R is the type, and they sound extremely similar. But you know, reflexive R is the true-false statement. We can do that here. Like we can click on reflexive R. We can see it's a prop, right? Reflexive R is the statement. We're trying to prove the statement. And R reflexive is the term. It's on the other side of the colon. So this would be exact. Exact R reflexive there. I mean, if we were doing this properly, we could do that. And now, of course, we've still got to. You see, split. If we go back here, you can see that this looks like this and this and this, but actually there's brackets somewhere. If we hover over the first and, we get all three. If we hover over the second and, we just get two. So the brackets are there, and that's why split did that. And so now we need to split again. Split there, and then this is exact R symmetric. And oh, hard luck. Oh, I got crazy brackets. There we go. Exact R symmetric and exact R transitive, and that should do it. There we go. So we've solved all the sorries in this level, and you know, as a bonus, we can define a term of type setoid Z. A term of type setoid Z is just a pair of things. It's a binary relation and a proof that it's an equivalence relation. So that's what S is, just the binary relation, and R equivalence is a proof about R, right? So S is R and the proof all bundled together into one object. And then we can take the quotient. So in Lean, you take quotients by terms of type setoid, and so we take the quotient by X, and now we've got Z mod 37. And that's the end of this video. Thanks for watching.